So I put this quote on the first slide. You can ask me, what does Heidegger has to do with machine learning workflow in sciences? The thing is, we can do almost everything with machine learning today, and this is what I will show you in the talk. The one thing that is remaining and which interests me is how do we choose what we work on, you know? And it's interesting for me, you know, I'm getting 50, you know, I have to sort of decide what to do with the rest of my career, but it's also interesting because AI is starting to do a lot of things in science. And one question we can ask, you know, if we can do inference, we can do simulation, we can do data collection, is how AI will choose what problem to work on. And this is sort of an interesting question that I will address at the end of my talk. So in general, we are all problem solvers. How do we decide what problem to work on? Okay, so this is sort of frames the subject of my talk. You will see there will be a lot of interesting angle of this question. So the first part will be about our activities on trying to put machine learning in scientific workflows. What are the particular challenges when we want to put machine learning in science? How do we do this reproducible workflow building? Some of the examples and the ramp tool that Florent mentioned. And the second part of my talk will be about this question of how do we use machine learning for automate hypothesis generation. So I'm the director of the Center for Data Science at Paris-Saclay. It's a horizontal project funded by Paris-Saclay. The goal is to manage, structure, work on tools for this data science ecosystem, which is partly consists of people in data science, so machine learning, signal processing, statistics, visualization. The other part is people who work in sciences and who provide data and who would like the expertise to work on the data. So we've been doing this since 2014. So I am in the laboratory of linear accelerator laboratory in Saclay, working with physicists. So this was sort of like a generalization of this experience with other people who work at interfaces with other sciences. And we started to work on how to organize this ecosystem, what tools we need to do, what are the missing elements to accelerate science in this particular case. So we have this landscape. So we have domain scientists coming with their data sets from neuroscience, economy, physics, astrophysics, chemistry, etc. We have data scientists, more or less us. And we also have tool builders, engineers. And this is an important segment of the ecosystem. It's very interesting that in France, we have a lot of research engineers. Actually, it's a position at CNRS and in RIA, and it's a nice thing to have. But the funny thing is that most of these research engineers work in domain sciences. If you look at computer science labs, there are very few of them, and most of them are doing system administration. So how to organize these things so that it works together? In data science particularly, we need those engineers to put the methods into tools which then can be used by domain scientists. The main problems are especially at the interfaces. One interface is what we call the data engineer, who is at the same time a data scientist as the software engineer. We have some of them in Saclay. And the other one, what I call data value architect, or this kind of data scientist who is not only technical in the sense that it knows all the methods in data science, but can also communicate with domain sciences, either with one or maybe like a generalist person who can actually go to somebody, formalize the problem, give it to data scientists, and organize the whole thing. So what are the challenges? There are management and organizational challenges and technical challenges. So I have this slide on the management challenges, which we answered with this ramp tool that I will talk about later. So lack of manpower. We have a huge brain drain to industry, especially people who can actually talk to business or the domain sciences. Misplaced incentives, so data scientists are not really incentivized to work on scientific problems. We are incentivized to invent new methods and show that they work, but the primary goal is not to solve problems on domain sciences. On the other end of the spectrum, if you really want machine learning to work on scientific workflows, somebody has to put them into production. So you need data engineers the same way you need them in industry. We have very few tools for managing innovation, and especially collaborative innovation where people from different domains get together. We usually do it very naively, trying to use the same tactics that we use in our narrow domains, and it usually doesn't work when you have people who don't speak the same language. And finally, the bottleneck is sometimes not data processing or data science, but more data collection and annotation. People are outside machine learning. They don't know what data they have to collect. The technical challenges are also very interesting. So a lot of them are maybe known in machine learning, but they are on the peripheries. So the specific, so one thing we discovered, or we sort of discovered and invented at the same time, is that designing the workflow with all the elements in it, that I will show you, is more important than actually solving the problem. Once you have the workflow, we can actually crowdsource the optimization, the hyperauto, even the algorithmic design to people who are not even experts in data science. The other particularity in science is that most of the time, or a lot of times, we use simulations to train the machines. So the data generation process is part of the design. Okay? In machine learning, if you look at any textbook, the first page starts with the IID oracle, which is a fairy tale, especially in this domain. In my opinion, it's also a fairy tale in industry and in the general well-known domains where machine learning is used, but in sciences it's especially important because it's sort of not part of learning theory that we have to design the data generating process too. One particular problem with this is the systematic uncertainties, which are very well known in physics but not very well known in machine learning. And we also have an opportunity. Most of the benchmarks in machine learning come from the bulk of the industrial products, speech, vision, video, language. We have a lot of interesting problems in the tails, and they have an opportunity to diversify the machine learning benchmarks. So I'll talk a little bit about this systematics problem. So in sciences, your estimators, let's say you want to do inference, they should not only be efficient, but also insensitive to certain variables that you don't know. There are variables that you don't know. Those are like you can't deal with them. But there are some stuff that you know that you don't know, and you can even model your uncertainty about those. And you want to develop inference which are robust to those unknown parameters. If you look at what experimental physicists do today, 90% of the time is spent on controlling these systematics. Systematics that come from the unknown physics, in terms of physics, but also the unknown things in the detector, so in the experiments that they design. These are very complicated engineering systems. It's unsolved and mostly unknown in machine learning that this is the main issue in putting machine learning in scientific workflows. The closest thing to this in mainstream machine learning is what we call fair ML. We want to make classifiers in an insurance company that's, for example, robust to skin color, because this is legally they should not be discriminating the loans they give or the insurances they give based on skin color. And this is a data generation. It's a problem of what data we use to train our machines. Now, simulation-based training is biased by design. Why? Because if we knew everything, we wouldn't have to do simulation. Okay, so there are unknown parameters in the simulation and the distribution from which we simulate the data, which we would like to infer. If we knew everything, there wouldn't be need for simulation. So some, cartoonish picture. So this is a typical situation when simulation is shifted with respect to real data. you want to learn inference, so a supervised learning problem, like, separate Higgs boson from background. But you don't know, where the data will lie in the X space. And what happens is you get a biased estimator, of course. Okay? And if you look at, where this projects the data, it will be shifted with respect to Y. Another funny situation, and this has actually happened, this is an anecdote. Say you want to measure the energy of a particle, you shoot it into a calorimeter. Calorimeter is some kind of device that measures some signal about the particle. Today you have this so-called pixel calorimeter, so it's like a big picture, a 3D picture with voxels in it. You shoot a particle in it, the particle makes a big, what they call a shower. And so in every pixel you measure some sort of signal, and you want to infer the energy of the particle from this signal. Okay? So what you do is you simulate a lot of particles, and you learn a function from the signal to the energy. And what physicists do, because simulation has to be organized, it's a complicated process, they like to bin the values of the energies on which they simulate. It's easier to do. Okay? So for example, they generate data on 2, 4, 6, 8, and 10 GeV. They shoot these particles in the simulator, they measure the signal, and they learn a neural net or a boosted tree to infer the energy, and then they use this on real data. Okay? So what happens is that since these neural nets, these boosted trees, are so powerful inference machines, it can actually learn that the data was generated in bins. Okay, so when you look at, uniformly generated energies, you get this kind of function between what's predicted and what's real. Okay, so this is just another example that you have to be very careful when you start working with powerful machine learning algorithms to do these things. When it's, a linear function, usually it interpolates between, because you have such a big error on the estimate that you don't see these levels. But when you give it to a neural net, you can have this sort of phenomenon. And this is, again, nothing to do with machine learning. The neural net works perfectly. If you think that your data is binned in real life, then this is what you should do. The problem is not the neural net, and it's not overfitting either. This is another phenomenon. The problem is that the distribution on which you learn is not the same as the distribution on which you test. So to summarize, the systematics is exacerbated by machine learning because it's so efficient in optimizing the score. So one problem of addressing this issue is that the systematics is not an event-wise score. It's something you can also only treat on distributions. So putting it into the machine learning pipeline is difficult. The most similar stuff that's happening in machine learning is these generative models called GANs. And actually the work of Kyle Kramer and Gilles Loup is based on, it's a similar way to address systematics to what people do in GANs, where also the problem is to sort of match distributions. The classical approach to machine learning has been used in physics since the 90s. So the Higgs boson discovery, but all the particles before already used not neural nets, but mainly boosted trees. Why? Because you had to be very fast. Because the only way to tackle this systematics for them is you take all the unknown parameters and you use extreme values of them, and you train on one distribution and you test on another distribution and you check the differences of your estimate. Okay, and then you do this for all the different pairs of different combinations of those values. So you have to train like 60,000 neural nets or boosted decision trees. And if you want to do deep learning, even one big net is really slow. So this is why they preferred inference algorithms that were fast. But it's already been done. The only problem is that the only way to tackle this problem is this brute force check. And this also that would measure the systematics, so you can report it correctly, but this doesn't optimize your estimator to be robust to those parameters. So these are open research problems. So this was just one of those technical questions that you see emerging because you want to put ML in science, and which is perhaps less known in mainstream ML. We work a lot on machine learning workflows in sciences, and we identified 4 different use cases of machine learning in scientific workflows. The first one is data collection. You want to replace a human annotator or an algorithmic collector by an algorithmic collector. For example, we have a pipeline on labeling insect photos that people take in their garden for ecological studies, or detect Mars craters on satellite images that orbit around Mars, detect particle tracks in physics. So these are very important problems. Perhaps epistemologically, this is the least interesting. It's not, it's just a tool. The second one is inference, and perhaps this is the most well-known use case, is when what I described with measuring the energy of the particles. So basically, you have a forward generating process from some small number of parameters towards some bigger image, like a detector. LHC has like 1 million electronic channels. And then from this observation, you want to reconstruct the generating parameters. The third one, which we are starting to get there, is actually replacing the forward model. So when we start to generate data, not using a physics or a first principle-based simulator, but a neural net for certain reasons that I will explain. And the fourth one, which is probably the moonshot thing in this talk, which very few people actually aware of, is that we start to do generative models, machine learning models, not for generating signal, but for generating hypotheses. Okay? So what hypothesis should we test? And this is where it gets interesting epistemologically. So some examples. So data collection, I mentioned this. We got 150,000 photos from the Museum of Natural History in Paris, labeled photos, labeled by people. Interesting one because a very, very heavy tail. So the last 100 classes of these 400 classes had only 10 examples per class. It's a very nice benchmark for transfer learning or few-shot learning when you want to learn a class based on one example. And we have very nice results. So we have 90% accuracy, total accuracy on these 400 classes, which is really, really great, using, of course, the latest deep learning, ImageNet, transfer learning solutions. Another deep learning, yes?
This is what is called supervised learning.
Yes, completely.
Yes, because you know what it is and try to minimize that.
Yes. Yeah, so most of except for the last one here, it's all supervised learning, where you have X and Y, and you just want to learn a transformation between them. So for me, machine learning is just an engineering tool for inference or learning complicated functions based on input-output pairs. The last one is not. So that's more interesting. It's what you call unsupervised learning, but I don't like that word because it covers a lot of things and you don't know exactly what it is. So the second one, this was also a sort of workflow where deep learning shined. It's a little bit more complicated than classification. It's the detection problem. You have this sort of cropped images of the surface of Mars. A graduate student took like 6 months to a year to find all the 200,000 craters on Mars, and this is what we would like to accelerate, maybe to go to another planet, by using this labeled data to design an algorithm that finds those craters, estimates their center and radii. So this is an ongoing challenge. I will actually reopen it for summer school in a couple of months. Inference. So this was a challenge we ran with astrophysicists on light curves of variable stars. So there are these stars which change luminosity in time. The raw measurement is the blue and the red dots. It's 2 filters. And the goal was to find the type of the star. Roughly, there are 2 kinds. One is an eclipse system, where one star goes in front of the other, so the total luminosity decreases. This is what you see on the right on the bottom. So this is a very nice signature when you see the eclipse. It's also the same sort of workflow is used for discovering exoplanets. And the other type, you have several subtypes, is the pulsars, which change luminosity by physical processes in themselves. The pipeline was interesting because we didn't have, of course, the smooth functions. We only had the measurements. So there was one first step where you had to fit those measurements, and the second step where you had to read out features of the function and classify the stars. This is an ongoing challenge. It's healthcare. It's with a collaboration with a neurologist in Institut Pasteur. Huge data collection effort. So if you work in healthcare, you know that sample sizes are usually in the hundreds, and they are very scattered because hospitals try to keep control of these samples. So for this challenge, we managed to gather more than 2,000 patients, which is more or less the minimum that you should have if you want to do any significant study on machine learning, because the problem is not even the training, but the test. If you have less than 1,000 points, then the Poisson fluctuation kills your significance. So the data is very interesting too. It's very expensive actually to get this data. Patients have to stay at the hospital. fMRI is expensive too. So these are 3D movies of brain activities. So fMRI measures brain activities in the tiny voxels of a millimeter size, and movies of those. Okay, then we have treated the data, so we don't give these movies to the people because every patient would be a gigabyte. But there are sort of steps that are involved in the data processing that we are not giving to the challenge participants. The goal is to classify healthy patients and autistic patients. So the idea is that if we can do this, then you could actually see whether there is any signal in these signals in terms of, detecting autism. So it's ongoing. We have money prizes on this, and the deadline is July 1st. So if you have students who want to do this kind of things, it's open. We had another project, which is the first one with the publication. Actually, it's probably also the first paper where all the machine learning was crowdsourced to students. So all we did was setting up the workflow, the scores, but the actual optimization of the inference was done by students. Also major data collection effort. So this was about molecular spectra in the pharmacy department of a hospital. They want to, for quality control, they want to check for chemotherapy solutions, what's inside the solution before administering to patients. And it used to be that it was in an open IV where you could take a dropout, put it in liquid chromatography, and measure the composition and the dose. But today we have these sealed elastic bags, and it's very nice because the patient can go home with it and it delivers the drug during a week. But you can't open it anymore, and you really want to check what's inside because these are really toxic drugs. So if you overdose it, the patient can die. If you underdose it, it will not cure the cancer. So people start using these laser spectrometers to measure the composition of the solution, which are designed for food industry. So they are really good to measure like sugar level, but these complicated proteins have spectra which are hard to separate with the linear classifiers that are used that come with actually the spectrometers. So they gave it to us and asked us if you can use machine learning to do this. It was a complicated workflow, as you see, because you had to measure the dose and the type of the molecule at the same time. We had great success almost at the specification that they wanted. So now it's like in the second round where they try to convince the hospital to get more data and to sort of industrialize this solution. Then perhaps the flagship of these problems was the Higgs boson challenge that we ran in 2014. So LHC is this detector, accelerator, and 4 detectors in Geneva. The detector is like 25 meters times 44 meters in size. You see the people standing there. And the phenomena that you're looking at is on the millimeter scale that happens in the middle. So two proton beams collide and they generate hundreds of, so first you have hundreds of millions proton-proton collision every second. These are beams of protons that go with the speed of light around this detector. There is a strong, real-time classifier they call the trigger, which filters this 100 million to about 400, huge rate, which is then saved. Okay, so about 400 events per second are saved on disks. So what's saved is sort of like what you see there is particles flying out from this collision. So the raw thing is like hundreds of particles, the decay products of the particles that you created with the collision. You have hundreds of thousands, even millions electronic sensors, but it's very sparse, of course. Every event touches only a few percentage of it. What you usually do, you measure energies of particles, angles between those checks, type of particles, electron, muon, etc. So at the end, using all this domain knowledge, you end up with about 30 to 40 features, what we call features, per collision. And what you want to see, whether these features suggest that there is something new, a new particle that was created, that was hypothesized, so you could also simulate from that, and this is why we can use machine learning to do this, or not. So the question is whether in this feature space you see Higgs boson or you don't see Higgs boson. So the goal is to optimize. So this is a nice project because it looks like classification, but the actual goal is slightly different. So we had to really sit down with them and design the score. The goal is to optimize the expected discovery significance. You want a function that makes the Higgs boson grow as a signal, if it's there. If it's not there, you will not see it. But if you're not even sensitive to it, then you won't see it anyway. So it looks like a classification problem. You want to separate background. What we call background is all the other events that we know already, from the Higgs boson. So you want a function that separates those two distributions. The problem is when you multiply it by the flux and time, you end up with this. The Higgs boson is very rare. On the left, we simulated the Higgs boson, but from a 50-50 distribution. So the chance of a Higgs boson was 50% with respect to all the background, when in reality, the chance of a Higgs boson is really, really low. So when you do this, the signal disappears, which means that actually it's epistemologically interesting, because you would think that we discovered the Higgs boson because somebody took a photo of an event that was the product of the Higgs boson. Well, nobody can do this today, because even the event, which is most likely a Higgs boson, which is on the right side of this function, looks more like background. Okay, so nobody has ever seen a Higgs boson, and nobody will ever see a Higgs boson in this sense. Yet, we can still claim with high significance that this Higgs boson exists. So how do we do that? Well, we don't use this function for classification. We use this to threshold, to filter the events. The pretty high threshold there, which is you see the red curve, and the red curve has a maximum. So the red curve is the score that we designed, and the threshold is actually the maximum of the score. So what does this threshold do? We just start counting the events in this bin on the top. Okay? So we select the events. And from simulation, again, we know that the number of background events is about 100 a year. And this is a real number. So among this 100 million per second, the number of Higgs boson we see is about 100 a year. So if we know that the expectation of the background, not Higgs boson in that bin, is 100, and then you see 150 events, then you know that something is wrong. And since your only hypothesis was that it was the Higgs boson, this is how you claim discovery. And if you look at the numbers, the Poisson fluctuation of 100 is plus minus 10, so 150 is 5 sigma. So this, when you see this 5 sigma, this is when the publication goes out. The problem is, of course, which we didn't tackle in the challenge, is that this 100 has a systematic error. It's 100 plus minus something. And this has to be dealt with when you publish. So it's not so simple. But in the challenge, because it had to be simple for data scientists, we had to make it disappear, systematics, which is why the Kégl challenge that we run is not really useful for physicists, but that's another story. So if you look at the formula, what we want to optimize is signal over square root of background, which is similar, you know, if you have a good AUC, then you probably have a good S over square root of B, but it's not exactly the same thing. And this is called AMS, and this is how we measured success on the challenge. So this is an example where it looks like machine learning, but you really have to sit down and figure out what your real objective is. So this was the inference. Now, but as I said, we also have machine learning in generation, the forward model. So we don't want to replace simulation, and this is coming. Most of the time for cost cutting. If you know the function that generates the signal given the parameters, you, for example, know where to put your temperature sensors in the sea, if you do this correctly in simulations. Sometimes you want to design your detector, your experiment, and in this experiment you have to do the reconstruction, the inference, and the simulation. And if it's slow, then the optimization loop is slow. So if sometimes you want to accelerate simulation, it doesn't have to be perfect, but it has to be good enough so you can optimize your detector design on this. And finally, sometimes you want to replace manual labeling by simulation. So you simulate from this type of event, this type of event, this type of event, and the type is actually the label you're looking for. So we had one workflow of this type. We wanted to predict the El Nino temperature based on simulation. So this is also sort of like a model reduction. You can do this by running your climate simulator, but probably you can do it better or you can do it faster because all you are interested in is the average temperature on the Pacific Ocean, not the full map. Okay, so we have what we did, we have industrialized workflow building and optimization by actually separating them. So this was one of the things that we've been advocating, is that before you jump on your latest deep learning solution, make sure that the workflow, the score, everything is correct and your experimental design is set up correctly. Most of the research in machine learning today, it's not only even in scientific workflows, but in like mainstream machine learning, fails on this step, okay? There are a lot of problems in the tails of the possible problems where benchmarks are not really well known. Every paper uses a different data set, every paper uses a different score, you cannot compare methods. And this slows down research action. So once you did this, what we do with our tool is sort of optimizing graduate student descent. That means a lot of, machine learning today can be modeled like a big random search with a little of prior coming from theory, that it's mainly random search. And graduate students are just very good, like a big number of graduate students is very good for random search, better than researchers. That's our experience. So the project is funded by Saclay. This is the team. You can consider it as a data challenge tool where people submit code, not predictions. In Kégl, you submit predictions, and this is one reason why it's unuseful for the organizers. Most of the time, it's human resources and buzz, but we could not really use the pipeline of the winner because he wrote a deep learning package in Lisp that we couldn't compile. Okay, so this triggered us to do this, develop this platform where people submit code. Of course, it's restrictive, it's only in Python. But at the end of the day, we have a prototype. Otherwise, it's like Kégl. If you know Kégl, we have a leaderboard. The big thing is that we have to train all the models. So we have to sort of manage cloud behind. So it's a tool for collaborative prototyping. This is how it started. Then we realized that students love this because you can compete, but also collaborate and learn from each other. And the direction we are going into is a data science process management tool, which is really looked for in industry too. During these, 20 iterations, we synthesized, what is a data science workflow. And what are the things that are fixed, that we can fix forever, and what are the things that are moving inside. And it has 4 elements, 4 moving elements: data connectors that read your data, put into the first step; the workflow, which are, what are the steps you want to execute on the data; cross-validation, so how do you do the experimental setup, which is easy for classification regression, but for example, time series, you have to think a little bit. And finally, the metrics, the score types. And so we have this setup where you have a Python script, about 50 lines, that defines your workflow. The rest is constant, so we can really put the whole development and optimization into a pipeline. As I said, code submission lets you deliver a working prototype and let people collaborate. These are some statistics. We have about 20 challenges. You can go there and see it. And this is what happens. So this is one of the challenges on some physics data, anomaly detection, but we can repeat this, and every time the same thing happens. Every dot is a student submission. These were Polytechnic students, really good ones, but not data scientists. Okay, we even did this at École des Mines, where students had like a 1-week Python plus machine learning course. So they were really not, developed data scientists. They were novices. Every dot is a submission. The score is on the y-axis, and the higher is the better. The pink curve is the best score at any time. So you see it's about a 2-week interval here. The green curve, it's a little detail. We also blend the models. Since we have the code, we can combine the models, and we have our algorithm to do that. The blue part is where what we call the competitive phase. It's like Kégl, except they submit code, but they don't see each other's code. And the red part is where we open the leaderboard so they can reuse each other's code. So what we see is, first, there is this accumulations of models. In this particular challenge, deep learning, vanilla deep learning, hyper-opted, everything got about 67% accuracy. And it's really far from what you could achieve by actually looking at the features, engineering the features, understanding the physics, how those features were constructed, which the best students did, even the competitive phase. So you see these blue dots there. There were like 10 students out of 100 who figured out how to do this. And since they didn't see each other's code, the solutions were diverse. The green curve separated from the pink. This is what we call the diversity gap. So when your solutions are diverse, blending works better. Interestingly, when you open the leaderboard, so they start reusing each other's code, they actually beat our algorithmic blender. So when they actually blend the code, so they are better. So this just shows that with all this buzz around deep learning, there are a lot of problems where you really need human experts, even these like novice experts, to do better. Yeah?
The green curve was some kind of boosting, or?
I can talk about it. It's tricky because it's a very heavy models, very good models, strong models. So boosting doesn't work. It overfits in a second. The other thing we see is communication. Because code submission does not only allow us to deliver prototype to the organizers, but through the code, people can also communicate. So the arcs are whether somebody looked at somebody else's code or whether somebody reused it. We ask people to give like a quantitative reference to somebody else's code if they use it. So there was this person in the collaborative phase who reused 4 models. You see the 4 arcs there, combined them and made a big jump in the leaderboard. So everybody looked at what he did. And after that point, everybody was using his code. You see the blue curves there. So this is the sort of thing that happens on our platform that cannot happen on something like Kégl. So some, just for references, I just put some of the links here about the open source toolkit, the platform, the Slack channel, and some blogs that I wrote about data science process management. So this sort of ends this part of the talk where I talk about this tool and what we do on scientific workflows. And the last 10 minutes, I would just like you to show a problem which is unsolved, but which is the most interesting if you want to think about how machine learning will be used or AI will be used in science in the next, I don't know, Probably this problem is AI complete. So if we solve this, then we have general AI. So we can automate almost everything. Generation, inference, collection, etc. It's not even controversial, it's just work, you have to organize these things. But what about hypothesis generation? So what do we test? Like how people come up with the hypothesis Higgs boson, why was it accepted by the community, and how could we imagine to automate this, So hypothesis generation is crucial. I don't know if you see the elephant in the room. The problem with it is that it's not covered by the scientific method. Okay? Popper made a conscious decision of getting the hypothesis generation out of the scientific method because he said it was too tough. The whole 19th century was about trying to model this. Where do ideas come from? We have no idea, and it's really hard to make it formal. It's philosophy. Okay? So Popper said, okay, I don't care where the hypothesis comes from. I just give you the tool how to test it. And then the falsification, experimental design, etc. came out of it. Now, the problem is that we are getting into automated hypothesis generation. And this is not science fiction. The robot scientist, this Eve, exists. It's a robot for generating molecules for drugs. And if you think about each molecule is a hypothesis, whether it will work or not for the given illness, the whole thing is in a loop. So it's not only that the experiments are done by the robot, but the design is done by the robot too. So it actually automated the full loop of hypothesis generation and experiment. Okay, so this exists already, and this raises the question: how do we get those molecules? So it is crucial. It's not covered by the scientific method, but interestingly, this thing that is not covered by the scientific method is not new. It's not because of the robot sciences that we have this problem. It's already beaten us in social sciences, biology, and all those domains where the sample sizes are usually small. So this is how scientific method works. You come up with a hypothesis, you design an experiment to exclude it. Yeah? That's what Popper's designed. And then you use a statistical test to show that the data is unlikely to be generated by a world in which the hypothesis does not hold. Okay? This is how the Higgs boson was discovered. So the problem is that it's a statistical method. Rutherford did that if your experiment needs statistics, you ought to have done a better experiment. He was right. It's much easier to use the scientific method if your test is not statistical, but 0, 1. The problem is that without statistics, science would be over because we sort of went out all of this slam dunk hypothesis, So we need, LHC, you will never say Higgs boson. If you give up on statistics, then you give up on actually claiming anything about the world beyond those things that can be seen 0 or 1. So you have all these controversies about the p-value, Some claim that 30% of the social science papers are unrepeatable and wrong. There are a lot of technical issues around it, but the main problem is the tautology. Okay? If you have a statistical test that can have some false positives, and all your hypotheses are wrong, then whatever you do with your significance, all your positives will be false. You see what I mean? So if all your molecules are wrong, some of them will pass the test because of fluctuations, and they will all fall positive. You will have 100% false positive rate. So this is how you get the 30% actually in the previous paper. Okay? It's not about you can go to p-value of -10 to the -7. If your hypothesis is all false, it will be false positive. But of course, if all your hypotheses are true, you are not exploring. You're just claiming the obvious, right? So you need to give some space of false hypothesis, otherwise there is no science. So, of course, there are technical guidelines like register all the experiments, don't do underpowered experiments, put the significance bar high enough, but there is a fourth one, which is test only plausible hypothesis. And this is sort of undefined. What is a plausible hypothesis? You have to state it before you actually do the experiment, right? So of course, all science is about this, like the sociology of science is about agreeing on some hypotheses that are plausible. It's a soft process, and it's not modeled by the scientific method. On the other hand, if you want to put it to automated science, you have to model this. Okay? So what is a plausible, non-trivial hypothesis? How to measure plausibility? How to generate them automatically? How is it related to knowledge? You know, these are the sort of scientific questions on this particular domain. So in machine learning, we have these really powerful generative models that look like generating stuff, right? We can use them to generate hypotheses. All you have to do is to make them digest scientific knowledge and use the process of like an autoencoder to generate new hypotheses. The thing is that most of these methods are used today to generate from a distribution. It's like sort of simulators. And here the goal is actually to go outside of what's known. So paradigmatically, we are in the dark. We don't want to generate from the distribution. We want to generate from stuff that looks plausible, but which goes outside of what you already know. So we have some papers on this, and the easiest thing we did was, for example, train on digits, a generative model, and test how many letters it generates. Okay, so this was like the start of an engineering framework to address this problem. And it's structurally the same problem as train on all music up to Beatles, and then test whether it generates Sex Pistols. Okay, so not a new Beatles song, but a new genre. Or if you go to industrial design, just take photos or engineering descriptions of all phones up to the iPhone and see whether your method generates the iPhone. Because this was the breakthrough, not a new Nokia phone, And if you go back to science, this is the question. You train, you design your method. This is not, the first part is not science fiction. We can actually get structural knowledge into neural nets, language, for example. So you train neural nets on all scientific knowledge up to Einstein, and then test whether it finds relativity theory. So this is just a snapshot of what we did on these characters. We designed generative models that are sort of crazier than what you usually optimize them on in machine learning, because people in machine learning, they have bedrooms, they want to generate bedrooms. Here we have bedrooms, and we want to generate new kind of rooms, right? So we have generative models that digest digits and generate all these kind of symbols, which don't look random, okay? And we measure the quality of these by counting how many letters we have in those symbols. And so in this way, you can compare the novelty generating capacity of these models. So you can read a little bit more about these in these links. And thank you.
Thank you. Naive question, going back to the part of your talk about the Higgs boson. And you said there is the trigger which selects, and if I remember correctly the figure, you select a very, very, very small part of the data. Is there a systematic bias in the way you select this very, very small part of the data? How can you check about, the systematic bias, which is the consequence of the selection?
It's a very good question. This is what experimental physics is about. That's why we have 10,000 physicists working on this, because they have to double-check, triple-check everything before they commit to a trigger. We have the trigger because of economy. LHC generates bigger data than the internet per time, So we can't save them. The disk space is very expensive, so we don't need to do those triggers. There are some schools or some ideas actually that we have to throw away all the data and do the analysis real time. Experiment goes in, paper comes out, or the histogram that you need for the discovery, because of this economics. So this is a very interesting thing. Of course, the questions are very similar to the analysis, The only difference is that the analysis, you can repeat it, whereas the trigger, you throw away the rest of the data. So before you design your trigger, you have to make sure that you don't bias system. You make the boxes, for example, large enough around the phenomenon that you look for. So if the phenomenon moves around, you still have it in the box. This is the sort of like ballpark explanation of how they do it, but it's a good question. This is why machine learning is not so much used for trigger, although formally it's completely a machine learning problem. Like, it's just keep it or not. It's a binary classification. It's like, detecting faces and images. But because they have to check the systematics, they have to look inside what the function is doing and double check all the systematics. So they prefer to do like more pessimistic, less efficient cuts, but which are more robust to those systematic errors.
I didn't quite understand what do you mean by generating letters from numbers. Because, well, I mean, there are symbols which we give meaning to, but any convention would work either for numbers or for letters.
True.
So how does this relate to the existing framework? And well,
I'm very happy you asked this. If you didn't have this question, I would be in trouble, actually. So the goal is not to generate letters. The goal is to have a proxy score, like a quality score, on which you can compare two algorithms. And the danger when you want to do this, I mean, you can have like an algorithm that just generates noise. You can have another algorithm that only generates a subset of the digits. This is actually what's happening in machine learning. Most of the time, when people generate bedrooms, they check whether the images are bedrooms by eye, but they don't check whether you got the tail of the bedrooms, all the modes. Because this is really hard to check, because since you don't have the distribution of bedrooms as a measure that you could use to compare distributions, you probably miss a lot of modes. So most of the generative models today are tuned to restrict what you generate to a subset of what you've seen, which is exactly what you don't want to do when you want novelty, right? So we give more freedom to these machines, but then the question is, how do you avoid that machine just generates complete noise? And one way to do this that you take, it's sort of like changing the cross-validation scheme. Instead of IID train test, you select a subset of the classes to train, and you look whether what you generate has some meaningful symbols, where meaningful is defined by the other classes. Of course, you can have several other ways to define classes. This is just one way to say that this algorithm generates more meaningful symbol by counting how many letters it generates. But the goal is not letters. You see, most of the symbols are not letters. If you want the scientific analogy here, all the characters here are the untrue hypothesis that turns out to be untrue, and say the letter is your experiment. Okay, that you don't know before. You don't know what a letter is, but you design your experiment. Okay, so by counting whether your machine generates some letters, you give a sort of plausibility score to the actual algorithm that did this. Okay, so it's not about letter generation, it's about comparing models for novelty generation capacity.
Hi. I have a question about the ramp. So you gave the example of how you call that, the grad student gradient or optimization. So this is very nice, but it doesn't seem to be very scalable. Like if you need to solve 10,000 machine learning problems, probably you cannot afford to have a week of Polytechnic student for each of the problems. So my question is, how do you scale that? And in particular, the big companies, they develop these auto ML stuff, so they try to mimic a bit the process of searching the space of models, optimizing that, and then being able to have the human out of the loop in a sense. So in your experience, do you think the human still has some added value in the process? This is what you pretended in your example, and will it continue like that?
It's several questions in one, so I'll try to answer each of them. It scales or not, I don't know, but you have to compare it with the classical method, which is write an ENS project, hire a postdoc, and in 6 years you develop 3 or 4 models that you publish. With respect to this scales much better. The second question is, of course, we do everything we can automatically. So that's another way to scale, like, hyper-opting random forest is solved. Hyper-opting neural nets is not really solved, but it's a technical question. I mean, you know what you have to do. It's an optimization problem. It's just complicated. Automating feature generation and feature engineering is where most of the breakthroughs happen on the ramps. So these are problems where you have to understand the semantics of features, scientific problems sometimes, and most of the things that we cannot automate happen there. This is our hypothesis now, but you are right that eventually when we learn how humans do this, as that's the AI paradigm, we learn how humans do it and then we automate it. So eventually all these things can be automated. For the particular challenge I showed you, it's probably AI complete in the sense that we give you a IPython notebook where the physics is described. You have to know physics, you have to know the Lorentz transformation to get these features. It's not theoretically impossible to have a neural net that learns the Lorentz transformation and understands text, but it's not today. So as of today, you still have space for human interaction. Yeah. And we also have research to done because of this, because at the end we will be replaced.
Where do ramp users typically come from? Are they like all from the same group in the school, or do you manage to have outside participants? And how do you manage having an increasing number of participants?
Yes, a lot of them are coming from our masters in Saclay and Min. We force them. But it depends. Like, for example, we are running this autism challenge today, and so the full worldwide neuroscience community signed up. I don't know if they will submit or they just interested in to see the code, but we have like, 10 subscriptions per day in the last 2 weeks because of the challenge we run. It's not a startup, so we don't have like, aggressive customer discovery and pushing it, although we are trying to get it into industry too. So we have some projects with Thales and some banks, but it's not the goal now. Okay, we have 1,500 participants. That's more than enough to actually have really good solutions, for example, for the pollinating insects. The other thing is, if you look at Kégl challenge, Kégl claims to have like 1 million users. Okay, people who have an account on Kégl. Out of this 1 million, there are about 10,000 who actually work on Kégl. And out of this 10,000, how many do you think actually adds to the solution something new on each challenge? I would say like a handful or maybe 100, but probably less. So what happened, for example, in the pollinating insect, we had 30 participants. 10 of them were really good, and 5 of them actually stayed for the collaborative phase and solved our problem. You don't need a large number of people. You just need a way to select the best and sort of incentivize them to stay there and work together.
All right.
The other response, how to scale this,
Okay, so if there's no more question, we should thank Balázs for his talk.
Thank you.